The overall state must be completely antisymmetric, and since the color, which is a singlet, the color part, which is a singlet, is by itself antisymmetric, the rest must be symmetric, as you see the configuration and the space part. And this implies that both of them are the same symmetric type, or both antisymmetric, or both mixed, or both symmetric. Now here I collected the non-strange resonance. This is an experimental spectrum taken from the particle data group. And I have collected in, I can arrange them in SF6 configuration. This is the nucleus, this is the delta, both for the fundamental 56 representation. Then you have an excited one, and a radial excited. Here you have the negative parity states, and so on. You see that the underlying picture is that there are SO6 invariant levels, and within these levels there is a splitting, which is of course due to some SO6 violation, which can be treated in some sense as a perturbation. I would like to notice that here the negative parity states are more equivalent at the same place or even higher than the first radially excited state. An observation to be kept in mind. Now to build the dynamics, we have introduced Jacobian coordinates, which are the standard Jacobian ones. But in our framework, instead of using directly rho and lambda, we have substituted the two vectors with these new coordinates. We keep the angular part, but then the two rho and lambda moduli are substituted with x, which is the square root of the sum of the squares. This is called the hyperradius. And the t, which is related to the ratio between rho and lambda. In some sense, x measures the size of the system, of the overall system, and t is a sort of deformation. These coordinates allow to treat the problem in a similar way to what is done in the standard two-body case, in the sense that you can expand any function, wave function, or potential in a series in terms of the so-called hyperspherical harmonics, which are a generalization to 6 dimensions of the standard spherical harmonics. These hyperspherical harmonics are eigenvalue of the operator, which in this framework is the Casimir operator of the O6 group, and the eigenvalues can be written this way. Gamma is called the grand angular quantum number, and describe the geometrical part of the wave function. The point is that already in the 80s, Haselbrand and other collaborators using two-body potentials for describing the equal system noticed that the behavior was very similar to a potential which was practically dependent only on x. And this has given reason to our hypothesis, the hypercentral hypothesis, to think that the three-quarter potential depends only on the hyperradius. In this way, as in the central potential case in the standard quantum mechanics, the wave function, the space wave function of the three quarters can be factorized in a hyperradial one, which contains the dynamics, and a hyperspherical harmonics, which contains the geometry. In this way, we have only one differential equation, which has to be solved in order just to have the wave function. This is the basis of the hypercentral model we have been done in general. I have assumed the particular form of the potential, a so-called hypercoulomb term plus a linear confinement term. This potential can be also considered in some sense the hypercentral approximation of a two-body potential like that, which is of course similar to the Cornell potential. There are also other motivations for introducing potential of this type, because since the x coordinate depends on all the coordinates of the three quark, so we may describe also three-body mechanism, which has introduced in some models in the past, and the situation in the case will be very similar to the Fuchs-Tube model instead of with this Y-shaped configuration instead of the triangular configuration. Now, there are two cases which can be solved analytically. One is just the hypercoulomb, the term, and one is of course, the harmonic oscillator is, we know it is solved analytically, but if you calculate this quantity, which appears in the harmonic oscillator Hamiltonian, this quantity naturally depends only on X, so it is naturally a percent. Here I depicted the spectrum of the harmonic oscillator, which was usually applied to these considerations, and the hypercoulomb. You see here in the harmonic oscillator that the order of the state is positive parity, negative parity, positive parity. And this is typical of any two-body potential. In the case of the 1 over x of the hypercoulomb 1, you see that the first shell contains both positive and negative parity in the second shell. So this means that in this limit, the first negative excited state and the first negative parity state are exactly degenerated. If you introduce the linear confinement term, of course, this degeneracy is modified, and this is an order of the level.